we're going to start chapter 7, which is a little bit more challenging than what we saw in chapter 6. So in chapter 6, you learn how to write formulas for ionic compounds, for molecular compounds. And then you also hopefully learn how to write the name of compounds based on a formula. So if you look at the formula of an ionic compound, you can write the name. And if the compound is molecular, you can also write the name. And also importantly, you should be by now able to tell me or to tell yourselves whether a compound is ionic or molecular. So remember, ionic compounds have a metal. Molecular compounds do not. So if there's no metal in the compound, then the compound cannot be ionic. It has to be molecular. Now, this chapter is going to be essentially about two ways of converting chemical matter into one form or another. So way at the beginning of the semester, we learned that we have these things called conversion factors, that we can make these conversion factors from equalities. That is going to have to be applied again. So we're going to have to remember how to make these conversions using equalities and then creating conversion factors. And importantly, we're also going to learn how the atomic masses in the periodic table can be used to calculate what are known as molar masses for compounds. And then from molar masses, we can actually calculate amount of compounds in grams, which is what we can weigh when we do experiments. Without a way of doing that, when we write the formula of a compound, we don't really have a way of knowing how much of that compound we need or we have or we obtained after an experiment. We're going to start by looking at a chemical reaction, perhaps not for the first time, but we really haven't looked at this in a very formal way, and we will right now. So here's a compound that, remember that hydrogen is a little difficult to tell whether it's ionic or molecular, metal or non-metal. So we're going to call this, off the bat, a molecular compound. So there's no metal there. In other words, hydrogen is acting as a non-metal. So it looks like water, doesn't it? H2O is water, but this one has an extra oxygen, so H2O2. This turns out to be hydrogen peroxide. Now that's the common name, because if we were to use the naming rules that we learned on chapter 6, we would be calling this dihydrogen dioxide. 2 hydrogens, 2 oxygens. But the common name is hydrogen peroxide. Hydrogen peroxide actually in many languages is known as oxygenated water, water with more oxygen. Now when you have this compound at home, if you have a bottle of hydrogen peroxide and you look at the bottle, it probably has an expiration date. And that is because this compound slowly decomposes into 2 compounds. So this arrow indicates that there's going to be a transformation. This is going to be converted to something else. Now that something else happens to be water, plain old water, and oxygen. So this is the decomposition of hydrogen peroxide. You probably have witnessed that if you have ever used hydrogen peroxide at home or at work. If you put a little bit of hydrogen peroxide down the sink, you may have seen that it bubbles, it fizzes, right? That bubbling is this oxygen. That's what is happening. Now, why is it happening so fast and not in the bottle? Because there's some compounds called enzymes. Enzymes are proteins found in living cells that make this reaction go super fast. And that's why you see the bubbling, because it's going super fast. Now, in the bottle itself, which is what we're picturing right now, it goes very slowly. It's happening, it's slowly decomposing into those two compounds, but at a very slow rate. So you don't see the bubbling when you look at the bottle. There's a problem with this. Now, if you look at it, we're going to begin to read these things going forward as chemical reactions. In other words, there's some change that is going on here. There's going to be many examples. This is just one. This happens to be called a decomposition reaction because you break down one molecule into two different molecules. We're going to learn later in chapter probably 8 that there's a number of different names for the different transformations. Now, this looks correct for the most part because it describes what happens to hydrogen peroxide very slowly in that bottle that you have at home. H2O2 becomes H2O and O2. The problem with this reaction, the way it's written, is that it doesn't have the same number of atoms of hydrogen or oxygen on both sides of the chemical equation. So for a chemical equation to be properly written, for a chemical reaction like this to be properly written, you have to have for sure two things. Number one, the right formulas for the compounds. If you don't have the correct formulas, then this becomes meaningless. Well, I'm telling you right now, these are the right formulas. This is the correct formula for hydrogen peroxide. This is the correct formula for water. And this is the correct formula for oxygen. They're correct. Most of the time in this course, I'm going to give you the correct formulas. You're not going to have to worry about it. Sometimes in one problem or two, I may give you a question in which with words, I'm going to give you the reaction. Let's say copper sulfate becomes copper sulfite. Well, that you would have to write the correct formulas, but that's going to be very rare. Most of the time, I'm going to give you the right formulas. Number one thing. The second thing that has to happen to have this correctly written is that you have to have the correct number of molecules of each compound. So let me repeat this. You need the correct formulas, which are correct right now, but you also need the correct amounts, how much of each you need. And if we start counting, and let's do it together, we're going to see that we don't have the correct amounts. How many hydrogens on this side of the arrow do you see? There's only two, right? Two. How many on this side? Two. Also two. So that's the correct amount. Hydrogen is not a problem. But let's look at oxygen. How many oxygens do you see on the left of the reaction? Two. How many do you see on the right? One? Three. Plus two, three. So we have a grand total of three. One in the water, two in the oxygen itself. So three total oxygen atoms on the right, only two on the left. That cannot be. Now, this is called balancing an equation, and it's part of this chapter, but it's also part of the next chapter. Meaning, now we have to do something before we can even proceed to make sure that we have the same amount of hydrogen on both sides and the same amount of oxygen on both sides. And the only thing that we can do is put numbers in front. Numbers here here, and or there. We cannot change the formulas. I cannot say, oh, I have 3 oxygens here. I'm going to change this to a 3. Because that's a different chemical. It's not the right formula. So I cannot touch the subscripts, the little numbers. I cannot change those formulas. But I can put numbers in front telling you the amount. How many of each do you have? So if you think, for instance, when you make, if you ever make pancakes at home, you know, maybe you come from a different part of the world where you don't make pancakes. You make something else. But I use pancakes because I think most people have either eaten them or made them. So to make pancakes, my household, me and my wife, what we do is we take 1 egg, 1 cup of flour, what else do we put there? 1 cup of milk, mix it all together, and you have 12 pancakes. Now, if I use 2 eggs, 2 cups of flour, and 2 cups of milk, then I'm not going to get 12 pancakes. I'm going to get 24 pancakes, right? This is the same idea. But before we can proceed, we need to have the right amounts. I don't know how many eggs is this yet. So let's see. What do I have to do to bring this oxygen amount to be equal here? Well, I'm going to have to put numbers and see what happens when I put numbers in there. I'm going to put a 2 here in front of the water. I'm going to say, I think I need to produce 2 waters from one of these because that's going to give me the right number of oxygens on both sides. But that doesn't. These 2 is telling you that you have now 2 oxygens here and 2 oxygens here, right? So that now we have 4 by me writing a 2 there. This is just by guessing, yes.
Does that also give you 4 hydrogens?
Correct, correct. It also changes the hydrogen. 2 times 2, 4 hydrogens. So it looks like I'm messing up, but I'm not. This is a trial and error effort. You're going to try numbers and see what happens. So 2 times 1, 2, plus 2, 4 oxygens. What can I do on this side to get 4 oxygens? Put a 2 here. If I put a 2 right there, let's count. So I have 2 times 1, 2, plus 2, 4 oxygens. 2 times 2, 4 oxygens. Now, let's take a look at the hydrogen because we messed it up before. 2 times 2, 4 hydrogens. 2 times 2, 4 hydrogens. So now it's balanced. It has the right amounts. Not only has the right formulas, but the right amounts. I didn't need a number here. That one remains a 1. Remember that this is a 1. Let me erase the boxes because we want to now read these properly written reaction. And I'm going to use a new word that you have heard before maybe in this course, but if you haven't, that's what half of this chapter is all about. When I read these, I'm not going to say 2 molecules of hydrogen peroxide. I'm going to say 2 moles. So the unit that I'm using here is called the mole. Plural, moles. So I'm going to read these again using the proper terminology. 2 moles of hydrogen peroxide decompose into 2 moles of water and 1 mole of oxygen. That's my 1 egg, 1 cup of milk, 1 cup of flour gives me 12 pancakes. 2 of these gives me 2 of that and 1 of that. You follow that? Okay. Now, what the heck is the mole? Can we go to the lab, get a scale out, and weigh 2 moles of hydrogen peroxide? Not directly, but there's a way. And that's what we're going to learn next. So I'm going to read this once again the way it's written, but then I'm going to try to answer the question that you're asking. When I put a 2 here, that I'm going to read as 2 moles of hydrogen peroxide. Okay? 2 moles of water. 1 mole of oxygen. However, and this is super important, I'm glad you asked that question. Check this out. And I'm just going to put it and then erase it. 2 moles of H2O2 contain, and here it gets a little tricky, but it's not a problem, 4 moles of H and 4 moles of O. So each hydrogen peroxide has 2 of each, right? Each hydrogen peroxide, 1 H2O2, has 2 hydrogens and has 2 oxygens. That's what the formula tells me, right? If I have 2 of these, then I have 4 and 4. If I have 6 of these, then I have 12 and 12. I'm converting in my head. But in answering Amanda's question, one of these guys, so if I were to rewrite this using 1 mole, 1 mole of H2O2 contains 2 moles of hydrogen and 2 moles of oxygen. In other words, the formula tells you the number of moles of each element, of each atom. And we're going to need these for what we were going to do with this periodic table anyway. Okay. Now that we know what is the mole, it's just a unit of chemical measurement. We need to land it, we need to make it a real unit of measure. We need to relate it to the gram. Because moles we cannot weigh. I cannot come and get a scale or a balance and put hydrogen peroxide and read the screen and say, oh, I have 5 moles of water, of hydrogen peroxide. The scale doesn't know what a mole is. The scale only knows what a gram is. So is there a relationship between grams and moles? And the answer, yes, there is. That relationship is the atomic number. So let me take a look at hydrogen. There is hydrogen. So the atomic mass, I said the atomic number, but it's atomic mass. So hydrogen has an atomic number of 1, but it has an atomic mass of 1.008. Well, so far, I have called these AMUs. I don't know if you remember that, atomic mass units. Starting today, we're not going to call them AMUs. We're going to call them something even more useful. So this number is grams per mole. Super important that you understand that. So 1.008 grams of hydrogen are the same thing as 1 mole of hydrogen. That's what this means. So I'm going to put a little table here. Hydrogen, 1.008 grams per mole. Oxygen, now let's click on oxygen. So this is the atomic mass coming from the periodic table. And it says here 15.99 grams per mole. So I'm going to copy that over here. And I can turn this off for a few minutes because we need to understand what that means. I can rewrite this down here as follows. And watch carefully. 1.008 grams of hydrogen are equal to 1 mole of hydrogen. That's what grams per mole means. It's an equality. And you know that from every equality you can get a conversion factor. In other words, this is saying that 1.008 grams of hydrogen are the same thing as 1 mole of hydrogen, or 1 mole of hydrogen weigh 1.008 grams. And I can do the same for oxygen. I'm not going to do it because I think it's obvious. But that's grams per mole means 15.99 grams are equal to 1 mole. So the mole is related to the gram by the numbers that you find in the periodic table for the atomic masses. Okay? How is that useful here? How do I know what this is in grams versus what this is in grams and what that is in grams? Well, now we move to a different level of complexity in which we need to calculate something called the molar mass sometimes is known as the molecular weight, and unfortunately it has another name. So it has like 3 or 4 names. Formula weight. I'm going to use molar mass just to be standard and just to use one thing. Now the molar mass is defined as the sum of all atomic masses in a compound. That's the definition. It's the sum of all atomic masses in a compound. So with that definition, we can calculate the molar mass of H2O2. Okay? So molar mass of H2O2. How do we calculate it? Well, we need to add the molar mass of hydrogen and the molar mass of oxygen, right? That's what this definition says. So we're going to write it as this. We have 2 hydrogens times the molar mass of each hydrogen. So it's the number of hydrogens multiplied by the molar mass of hydrogen, right? And that's going to give me a number. But I'm not done because hydrogen peroxide also has oxygen. How many oxygens in 1 unit of hydrogen peroxide, in 1 mole? 2 oxygens, each of them weighing 15.999. When I do those 2 calculations and I add them up, I have the molar mass of hydrogen peroxide. So let's do it. And hopefully you have a calculator that you can help me do this with. Hopefully you have, for the first one, 2.016 grams per mole. That's the contribution of hydrogen to the whole mass of hydrogen peroxide.
And all of these are grams per mole?
Though all of these are grams per mole, because they are molar masses. First, a molar mass of hydrogen itself, then the molar mass of one oxygen itself, and then multiply by the number indicated in the formula. The grand total of all of these is the molar mass of 1 unit, 1 mole of hydrogen peroxide. So what is the molar mass of hydrogen peroxide? Well, I'm going to see if I can do it by hand. 4, 11, 10, 2, 3, 4. So 34.014 grams per mole is the molar mass of H2O2. Now, let's do one more calculation, and then I'll show you how. You're not going to have to be doing this for every molecule that you have. You're going to use a smart tool, the internet. So let's get the molar mass of water. Now it's only H2O. I think you know that that is the answer for hydrogen peroxide. Now let's do it for water. Water has also 2 hydrogens. So 2 hydrogens times 1.008 grams per mole. But it has only 1 oxygen, not 2. So 1 oxygen times 15.999 grams per mole. So this one is easy. This one we already have from over here, so I'm just going to copy it, 2.016. I'm going to add them together, 15, 11 still, 3, 8, 18.015 grams per mole is the molar mass of water. Now to do the oxygen we do the same, but I'm not going to do it. So you have 15.99 times 2, so the molar mass of oxygen is actually 31.998. How does this relate to the equation, to this chemical reaction? Well, now that you know the molar mass of hydrogen peroxide, you can actually say, I can go to the lab and weigh a certain amount of hydrogen peroxide, and I know what I'm going to get of each of these in grams, not in moles, because moles are a little tricky. What I'm telling you is that the amount in grams here has to be equal to the amount in grams here. We cannot have more or less. We had to have the same amounts on both sides. And we're going to prove that. Now, when we read this equation in moles, we say 2 moles of hydrogen peroxide produce 2 moles of water and 1 mole of oxygen. Let's put that in masses. So we're going to convert moles of hydrogen peroxide to mole of H2O2, 2 grams. This looks maybe a little daunting, but it's not. It's not, because this guy right here is a conversion factor. Okay? Go back to the beginning of the semester and you'll remember that conversion factors arise from equalities. So, here we go. How do we convert 2 moles of H2O2 to grams? Well, we need to multiply it by a conversion factor, right? And the conversion factor comes from here. Because this right here, I'm going to put it down here, is saying that 34.014 grams of H2O2 equal 1 mole of H2O2. That's my equality coming from the molar mass. That number and this equality are the same thing. They're saying the same thing. Now, you know from an equality you can get 2 conversion factors. What we need to put here is the one that has the grams on the top and the moles on the bottom, so that moles cancel out. So if I look at that, I say, oh, 34.014 grams of H2O2 divided by 1 mole of H2O2 is my conversion factor. I mean, I could have done it a lot easier. Just multiply by 2 the molar mass. But I want you to know where that comes from. And this is where it comes from. So 2 times 34 divided by 1 gives you the grams of hydrogen peroxide that this represents. I'm going to put that number on top. What is that? 68.028. Right? So I now know that 2 moles of hydrogen peroxide weigh that much. So I'm going to put it here in grams. Now, because we're not gods, when I calculate the amount in grams of water that 2 moles represent, and the amount of oxygen that 1 mole of oxygen represents, and add them together, they're going to have to add up to that. They better, or we're in trouble. We did something wrong. Let's see. Let's do the calculation for how many grams are in 2 moles of water. So, second calculation here. 2 moles of H2O converted to grams. Well, I multiply 2 moles of H2O by a conversion factor coming from the molar mass of water. Right? I'm going to give you a cheat sheet in a few minutes that is going to make this a little bit more manageable. But that's the molar mass of water, so I'm going to put 18.015 grams of water are 1 mole of water. And that's going to give me grams of water. 36.030 grams. Remember, I didn't do the cancellation, but moles of hydrogen peroxide and moles of hydrogen peroxide cancel out, so we're left with grams. Moles of H2O2 and moles of H2O2 cancel out, so we're left with grams. Let's put this amount right here. And before we do the oxygen, let's see what this says. Well, it says that 2 moles of hydrogen peroxide gives you 2 moles of water and 1 mole of oxygen. We knew that. But it also says that 68 grams, 68.028 grams of hydrogen peroxide produce 36.030 grams of water. And we need to do the oxygen. Now, as you can imagine, and maybe you should do this as an experiment before we calculate it, how much does the oxygen has to be? We're not God. We cannot create or destroy. Exactly. So that number minus this number is the predicted number that's going to be. Let's see what that is. Can you do that? Yep. 68.028 minus 36.030. 31.998 grams. That's our prediction. Let's calculate it over here. 1 mole of O2 converted to grams. We want to know the grams. Once again, we know the molar mass of oxygen is right here, 15.999. So we're going to say 1 mole of oxygen. But wait a minute, we have 2 moles, not 1. You see that? That's tricky. That's really tricky. These 2 better be included in the calculation of molar mass, because we have 1 mole of O2, not 1 mole of O. So 1 mole of O is not really what we want, it's 2 moles of O. This and that are the same. 1 mole of O2 is the same thing as 2 moles of O. Almost sounds like a tongue twister, but it's not. Or a riddle, but it's not. 1 mole of O2 is the same thing as 2 moles of O alone. Times 15.999 grams of O per 1 mole of O. And that gives me 2 times 15.999, 31.998 grams. And that's what we had predicted. So the key here was to remember that 1 mole of O2 really is 2 moles of O.
So I understand that,
Huh?
but then it makes me confused for the other one, like the hydrogen. How I'm not doing 4 moles of hydrogen.
Because we already did the 4 moles of hydrogen when we calculated the molar mass for 1 of them.
Oh.
I mean, I could have done this for 2 of them, but you always need the molar mass of the simplest thing. We never calculated the molar mass of O2, so that may be the confusing point. That is simply this times 2. Now, let me give you, now that we have all of these and we agree that the equation in moles and the equation in grams are the same amounts, just different units. Let's see how we can actually do this in a streamlined way. So if you want to convert moles of any substance to grams of any substance, you're always going to multiply by molar mass. If I want to know how many grams are 5 moles of water, I'm going to multiply by the molar mass of water. So you just multiply molar mass if you want to convert moles to grams. If you want to convert grams to moles, because you need it for some reason, you divide by molar mass. Okay? And that's what I call the cheat sheet. But there's more to it. Because I sort of started in reverse in this chapter. I haven't told you how many atoms or molecules are in 2 moles of hydrogen peroxide. I mean, now you know that 2 moles of hydrogen peroxide have 68 grams. Or 1 mole of hydrogen peroxide is half of that, right? But if I wanted to ask you, if you wanted to answer, well, how many of these each, how many H2O2s really this is in molecules, which we cannot observe. You need a super powerful microscope that doesn't even exist. This is when something called Avogadro's number comes into place. Now the good news is that we're not going to use this very much, only to solve problems, but in real life you don't use it. So Avogadro's number is like a dozen by definition, but it's a different number than 12. So remember, if I were to tell you a dozen, you really immediately think 12, right?
Yeah.
Everybody knows what a dozen is, right? 1 dozen eggs, 12 eggs. 1 dozen books, 12 books. Avogadro's number is like a dozen, but it's a very different number. We've seen it before. 6.02 times 10 to the 23rd items. It turns out that 1 mole uses Avogadro's number as a relationship. So 1 mole of any substance contains 6.02 times 10 to the 23rd items of that substance. These can be replaced by atoms, molecules, eggs, etc. It's the same thing as the dozen, but it's a different number. So if I wanted to ask you, okay, so how many hydrogen peroxide molecules you really have? You have 2 moles, but how many individual molecules do you have? Well, we're going to simplify our lives by completing this diagram, including now particles. Number of items, where items means atoms, molecules, eggs, fill in the blank. If you want to know how many moles are in a certain number of items, you are going to divide by 6.02 times 10 to the 23rd. If you want to know how many items are in a number of moles, like in those 2 moles, you're going to multiply by 6.02 times 10 to the 23rd. And that's going to give you the answer. We're not even going to use it as a conversion factor, but that's what it is. You see that? This gives you two conversion factors. 1 mole divided by 0.2 times 10 to the 23rd, or 6.02 times 10 to the 23rd divided by 1 mole. And of course, this is items. So you see, all we are doing is, okay, if I want to get the number of moles in a certain number of items, I need to use this conversion factor. So I'm dividing by 6.02 times 10 to the 23rd. If I want to go from moles to items, I need to multiply. So I'm multiplying by that and then divided by 1. It's the same thing, but I'm making your life a little bit easier today by giving you this one. Don't try to understand this if it's confusing to you. I think it's super important that you understand how to do molar masses in this chapter. Not so important how to use these conversion factors. Use this cheat sheet. Simple as that. Now let's answer that question as to how many molecules of H2O2 are found in 2 moles of H2O2. So where are we in this chart? We have moles of H2O2. We want to know molecules, items of H2O2. So we're going to take 2, because that's what we have, 2 moles. And we are going to multiply that number by 6.02 times 10 to the 23rd. That's all we're going to do. So that's going to give us roughly 1.2 times 10 to the 24th molecules of H2O2. Just do the multiplication. 6.02 times 10 to the 23rd times 2. You need to use your calculator. You need to use your calculator, because otherwise, when you do the homework or the quiz, you're not going to know what to do. And I'll show you what I did with my calculator to get this number. And that's a lot of molecules of hydrogen peroxide. If I were to write this number, it would look like this. 1, 2, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I don't know. I can keep going. That's how much hydrogen peroxide is in 2 moles of hydrogen peroxide, each individual H2O. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's the real number. I have covered, I think, everything you need to know. And your head is probably spinning, because it was a lot of information. So now we need to use that information in problems so that we begin to feel comfortable with what is it that we have to do. Because we need to be sure that we are getting the right answers. Let me see. I actually had an answer to that. Problem 5, you guys. Is it still the same?
How do we put the answer? Do we put the whole thing? Part C?
It says 2 significant digits.
C? Okay, let me see.
Let me see what answer you have.
Well, it has more. So
Yeah, so
it
just
should
put two
be
significant digits. Remember the zero is not
0,
significant.
2,
1, 6.
7.
Is that a 9 or a 4?
No, that's a 4. Yeah.
Okay, so then it's 0.016. Uh-huh.
I just want to make sure. I like to make
Yes.
sure before I go home.
Absolutely. Okay, now we're in a different type of problem. This may be a little bit more challenging because look at this. Calculate each of the following quantities in 0.16 mole. Calculate the number of moles of carbon, and we are given that formula. So, let me raise that. I'm going to erase the board and explain how to approach this problem because it's a little tricky the way it's worded, but it should not be. We're just going to continue to use conversion factors, or at least the idea of a conversion factor. Okay, you guys, I really need your attention because this can be a little confusing. So here we have a formula, okay? I'm going to copy it here. C6H14O. So it doesn't matter what the compound is, but it's the formula of a real compound. Now, 1 mole of that has 6 moles of carbon, right? That's what it says. It has 14 moles of hydrogen, and 1 mole of oxygen. So 1 mole of these has that, and that. Nothing new here. That's what the formulas tell you. Number of moles of each element. But the problem wants to know how many moles of carbon are in 0.16 moles of this. Not anything else. So what do we say? Well, we have a conversion factor problem here. We need to do, we're going from moles to moles in this case. This doesn't help. So let's set it up. We're going to say we have 0.160 mole of C6H14O. And we want to convert that to moles of oxygen. Okay? Here is a conversion factor. It's 1 to 1. 1 mole of this has 1 mole of that. So if I multiply this by that conversion factor, 1 mole of carbon are found in 1 mole of C6H14O, I get the answer. Basically, I'm saying that because this is equal to that, I can use that as a conversion factor, and there it is. Did I lose you?
Maybe a little. That's okay.
Okay, so no, let's put it here. Let's put this into equalities. So the fact that I'm saying that 1 mole of this has these many moles, I'm also saying 1 mole of C6H14O equals 6 mole of carbon. 1 mole of C6H14O equals 14 mole of carbon, of oxygen. And 1 mole of C6H14O is 1 mole of, sorry, this is hydrogen. I made a mistake there. So that and that is the same thing as this. And each of these is a conversion factor. Well, it's 2 conversion factors, right? One with this number on the top, one with this number on the top. We want to cancel out most of that, so we're going to have that on the bottom and the most of carbon on the top. This one is easy because it's 1 to 1. You didn't even have to do all of this if you rationalize it that way. But if we do the math, we end up with 0.160 mole of carbon. That's the answer. That times 1 divided by 1. The next problem is the one that is going to be revealing. So let's put the answer so that you see that I'm hopefully doing this thing right. 0.160, and I need to put the units, mole, submitted. What? Calculate the numbers of C. Oh, it's carbon. It's 6. What the heck am I doing? One mole of this is 6 moles of this, so this is a 6. Oh boy, I'm so sorry for confusing you. This equality is the one that I'm using, and I use the wrong one. I use this one. 0.160 moles of this contains 6 moles of carbon. Right here. Right? So now we need to multiply 6 times 0.16. We still need this information, okay? Because we're dealing with the same chemical. But now they want the number of atoms of hydrogen, not moles. So let's first realize the following. So they want atoms. Let's take a look at this diagram. What do we have? We have moles, right? We want atoms. So we're going to have to do 2 things. First, obtain the moles of hydrogen that we have in 0.16 moles of this. Because we don't have 1 mole. We don't have 14 moles. We have 0.16 times 14 moles of hydrogen. You see, that's what this says. So it's a 2-step problem. Unfortunately, the number is not 1, it's 0.16. So what do we get when we multiply 0.16 by 14 in my problem? It's different in yours. Just follow along. 0.16 for me times 14.
And then that answer?
Yes.
You would multiply the same.
Exactly. 2.24 mole of hydrogen is what I have now for real. So now I am here. Now I'm going to multiply by Avogadro and get the right answer. The atoms of hydrogen in 0.16 moles of this compound. Practice, practice, practice. There's not going to be another way. So times is 0.02 e to the 23rd. I get 1.35 times 10 to the 24th. One 0.35 24. atoms. They give me the units this time. So we got it right. That's a challenge problem because it doesn't tell you exactly what it wants. It's kind of hidden in there. Lara, are you okay? Are you?
No, mine is wrong, so I don't know. I was trying to understand.
Well, we have time.
Yours is 0.160, mine is 0.150, but I was trying to do, that's not what you were doing.
Let me see. They're asking you for hydrogen, and it's the same formula though? Yes,
No, it's just 150,
it's the same
but
formula.
you have
Okay.
160.
So,
I did it here.
0.15 times
Mine is
14.
2.1 instead
Perfect.
of the 2.
And then that
And
times that.
That's what I did.
23rd,
Oh,
not 24.
That's probably why. That's probably why I...
Remember that you need a parenthesis, okay? Or you need to make sure that put this number first, the one in exponent, 6.02 exponent to the 23rd, and now multiply that by 2.1. What, can I see what it says?
It's just here I have it wrong. I think it's the 20,
okay.
it's 24 instead of 25. I had 25, it was 24. Thank you.
Well, that's what we are
So
trying.
you have to put moles, isn't it?
You had to put, when they ask you and they don't have the units, yes.
Okay.
Yes. Express your answer with the appropriate unit, so yes. Okay, submitted.
No, it's incorrect.
So what was the problem? Incorrect. Let me take a look. This is for carbon, and carbon, oh, you forgot to multiply. Oh, no, you did multiply by 6. Let me see how much you have, because it may be different for yours.
No, it's the same.
Let me see at the beginning, part A.
Oh. Oh.
Yeah, let's just go back. Chapter 7, homework. And I think this is problem 5. You have a different amount. You don't have 0.16, you have 0.17.
Okay.
That's the only problem. Yes.
I'm having trouble. Again, I don't know what I'm doing wrong. So mine is a different number.
2.8.
Mine is 0.2, which
Okay.
ends up being
2.8.
2.8.
Okay.
And now, but when I do
Let's
it
put
to-
let's put Avogadro number first.
I've done it, so that's the
Multiple ways. 6.02
6.02
times 10 to the 23rd.
exponent. 23
And now times.
what was it, 2.8, and it's
Uh-huh.
giving me a plus. It's giving me this plus every
Equal.
time.
It just means that it's positive.
Okay,
So it's
that's fine.
1.69 times 10 to the 24th.
Oh, okay. was
I
getting
think that's
confused 'cause
what-
of the plus.
I think that's all it all means.
Okay, so
I think that's all it means.
So let me just
Yeah, try entering it and see.
0.69, 10 to the 24.
Uh-huh.
This I have 1.69 and we have 24. Oh, okay, okay.
So that was the issue. How you doing, Amanda? You're too quiet. Hanging in there?
So what I've been doing is
Mhm.
how's that? Yeah. So what I do,
Mm-hmm.
because it's just the way I learn, I can't do this at the same time you're doing that. So
Right.
I write down what your numbers are. I follow your thing. I write it all down, and then
Makes
afterwards,
sense.
I go
Makes
back
sense.
to mine. I look at this for reference
Makes sense.
for how to do it, and
Right.
then I do it on my own with.
Please continue doing that, because I think, so this would be your guide, your tutor,
Right.
to when you go back there. Absolutely.
And I don't know how to use the calculator yet because I'm doing your numbers.
Why don't
But
you
that part
find,
I can worry about.
yeah, why don't you find, I,
And because I'm going to get a physical calculator, right now I just have an app.
Right, but you know what? With the internet, this calculator is working really well for me.
Right.
So maybe you just want a good internet calculator, not even an app.
Well, I mean, I got that.
Sure, but you know, I mean, that
Right.
looks fancy and it has all the keys and stuff. But that's
So
one
it's
more thing to
similar
learn.
Exactly.
And if you just go to something simple like an online
Yeah,
calculator,
that's what I'm thinking of, getting just a simple
you're
calculator.
always working here anyway. So the only problem is that you have to be switching screens. Now, I'll be happy to see if we can figure out how to use that calculator that you
Because I
got.
think I'm gonna get.
I'm going to get a
pretty sure
physical
I'm
one.
pretty sure I'm gonna get this one, which is
Not
a TI.
expensive?
It's a TI, but it's a less complicated version than
Okay.
the 84.
Let me see a bigger screen image to make sure that it has exponent key or something like that.
Oops.
Do you see an EXP key anywhere?
Well, it's got second, so that one probably.
No, that's not it. And this one, oops, this one would work.
So this one's not gonna.
I
must
just
be
don't
in
want you
there.
to buy one that is not gonna have it like super easy. Oh,
Right.
right.
That's the scientific notation one.
That's
Yeah,
it.
it's a tenth
That's
of
it.
an N
Yeah. So yeah,
times
get
10
that
to the N.
calculator. I think it will be interesting. How much is it?
It's like $20.
Yeah.
Not bad.
Yeah,
Hers
because
is
I think
fine,
this
but
is the
one's
key.
20 and-
So if you get it and you bring it next time,
Yeah, and I
I'll
can
be
work
happy
on
to
it and
figure
I
out.
can,
Perfect.
know,
Sounds
figure
good
out
to
how
me.
work it. But yeah, I'm gonna pick that up probably today.
Perfect. Okay. Let's do the last part, I think. So on part D, you essentially have to do the same thing. You first have to go from 0.16 moles of this to moles of carbon. In this case, carbon is times 6. And then times Avogadro's number. So I'm going to skip that one then, because it's exactly the same as part C. See, you guys, so far, we've been able to answer almost every problem in the homework with what we covered, with the exception of this last one. There was a little bit of a mini lecture there.
So the only thing for this that I have a question on is for the units, how am I typing grams per mole? Because it's asking for the molar mass.
Okay,
So-
let's take a look. Let's do it.
Okay.
Because I do not know off the bat, I have no idea.
Input it, okay.
So we'll manage it when we get there. All right. So I'll wait until you guys are ready for the next type of problem. I'm going to wait a little bit until. You ready, Anne-Marie?
Yeah.
Okay, so can we move to the next type of question as a whole group class? This time, we are going to be doing, I think, something easier, calculating molar mass. We learned at the beginning of today that the molar mass is simply the atomic masses of each element in the formula added together. Here we have N2. So that means that we have 2 moles of N for every 1 mole of N2, right?
Yep.
So if we go to periodic table, oops, where was it?
14.
And we look for nitrogen, we have 14.007, but that's one single nitrogen, so we need to multiply that by 2 and that's going to be 28.014 for my problem. I don't know what you guys have on yours.
My first one is O2, which we already did.
Okay, and the question was from Rachel, so I have 28.014, the units. I'm hesitating here because I hope they don't expect AMUs. So I'm going to put gram per mole. Now, there's two ways of doing it. I don't know which one is going to like better. So I can say G divided by, oops. What did it do? I don't know what it did. Okay, let's see. Templates. Maybe that one. G mole. I don't know if that's going to work. So here we go. This is a trial and error for me. Submit.
Oh, yeah.
It like that one. Let me show you the second one though. So let's take a look at this. Now it's a little bit more complicated. The molar mass of NaH2PO4. So let's break it down. NaH2PO4. The molar mass is calculated as follows. Now you guys may have a different question, but I'm going to go with this one. So we have one sodium only, times the molar mass of sodium. I'm going to set it up all and then I'll copy the molar masses. Two hydrogens times the molar mass of hydrogen. One phosphorus times the molar mass of phosphorus. And four oxygens times the molar mass of oxygen. And then I'm going to add all of that together. So I remember this one 1.008, I think. 15.999. And then I need to look up the other two in the periodic table. What do I have? Phosphorus.
Do I have to write, if the atomic mass is very long, we have to include all of the numbers?
I will go with 2 decimal places.
Okay.
Yeah.
For
30.974.
phosphorus, it's long.
Yeah, the one that I'm looking at has only 3 decimal places. So 30, if you want, Rachel, do it with just 97, 30.97. Let's see how far we get from the right answer. And then one sodium, 22.990. Okay, so 22.990, 2.016, 30.974, and then, oh man, that's gonna throw me. 15 times 4, 15.99. What did you get, Amanda?
Oh, no, I just, on my periodic table, the atomic mass is 22.98.
Not
Oh,
167.
oh, it's different, huh?
But I think I'm just looking at the wrong number.
Wait, maybe not. 63.
For NA.
Yeah, it's a long.
What did you get for NA?
First, it's 22.989.
Okay, it's fine. Mhm.
Which rounds up to 992.
Yeah, you got the right one. Uh-huh.
And then you're just adding all of this together.
Yes. You have the same chemical, Lara, or different?
No, I have a different one, but I'm doing this one so I can know how to do my.
Okay. Perfect.
I got 823.928.
800?
Mine is 119.976.
Mine is 119.976.
I must have did something wrong.
So we match. Rachel, check it out. I mean, maybe you had a 4 here or something. Yeah, so 60, 90, about 100 and something.
Oh, the last one. I did the last one wrong.
What did you put?
For some reason, I don't know what I messed up on. but
Maybe
the last
40.
one I
Oh,
put
maybe 40.
700 something. Yeah, I
Ah.
probably put 40. That's probably
Yeah,
what
because
I
it's
did.
4O. I always worry about that. The 4 oxygens looks like a 40.
That's what I did.
I
That's
all
why I
I
had this big
I
number.
I always worry about that.
Oh, my goodness.
Yeah. No. It makes sense. Okay, so I'm getting 119.976. Okay, everyone. So we're going to put that answer. But before that, remember that you can double check yourselves with Wolfram Alpha. Just go to Wolfram Alpha and put the formula. So what is the formula? NaH2PO4. According to Wolfram Alpha, it's kind of hitting here is 119.98. We ended up with 1.19976 or 98. Okay, always double check because, you know, when, yes, Amanda.
So my last thing, once we get the 119.978,
6,
whatever, what is it just atoms, is it mole, is it grams?
It's grams per mole.
Okay, that's what I thought, I just wanted to.
But I'm glad you're asking that because I want to explore the second way of putting units. So 119 point, what did you say?
76.
76, 976, sorry.
Oh, I thought you said the 9.
Yeah, no, I don't, I think I didn't. Okay, here. So 2 ways of putting the units. The first one that I did was with this one. So I used, sorry, this is not very clear when this is up. So the first one, I used this one. This time I'm going to see if I can do the following. The units are grams per mole. So I'm going to put G. But instead of putting divided by, I'm going to put this period, which means times. And then I'm going to put mole. But here's the key. I need to put an exponent on that. And that exponent has to be -1. When you have a -1 exponent, mole raised to the -1 is equal to 1 divided by mole. It's per mole. So this and per mole are the same thing. Little confusing, I know. So stick with what is not confusing. This is not even chemistry, but I think it's going to pick it up. Yeah. See, in fact, if I go back to the first answer, that's what it did. It changed mine in per mole to mole raised to the negative 1. So anything raised to a negative 1 means per. So if I have in density, you guys remember density grams per milliliter? So I can write grams per milliliter like that, or I can write grams times milliliter negative 1. It means the same thing. Anything raised to a negative 1 means it's on the denominator. Okay. So let's see.
Looks tricky.
Well, you know what? I'm glad it's tricky because we haven't talked about parentheses. And although we did in chapter 6, we haven't here. So IFE parentheses CLO4 2. Okay. So let's interpret that one. Just like in math, anytime you have parentheses, everything that is outside of the parentheses is affecting what is inside of the parentheses. Yes?
We add this. When do you add the minus 1?
When it's like this is the same thing as like that.
Also, it doesn't matter.
It doesn't matter. So if you enter it like this, the computer is going to turn it into this because this is, yes. They're the same thing. So per mole means mole negative 1. Okay. So when you have a parenthesis, here we go. There's no question that there's only one ion, right? Yeah. So I'm going to start tabulating here. One ion. Now, these two affects the entire thing inside. Yeah. This is chlorine, Cl. Only one. Times 2, we have 2 chlorines. Okay? This is oxygen. There's 4 of them. But there's a 2 outside the parentheses. So 4 times 2 is 8. 8 oxygens. And that's what we're going to go with. Now we're going to, oops, I'm going to put a line here because it's not 80. So times, we're going to find the periodic table that I've been using today. Iron, 55.845. All of the units are grams per mole. Chlorine, 35.45. And oxygen, we've been using 15.999. So 55.845, 70.90, and that one I don't know. Okay. Thank you, Lara. 127.992. We add all 3 numbers together. So plus 70.90 plus 55.845. Right, so we all agree. Perfect. Grams per mole. Okay, so 254.78 is what I'm going to enter. 254.78. 254.78, I think. Oh, 74.
That's what I have too, yeah.
74. Sorry. And grams per mole. I'm going to use the template again just to show you how it converts it. Grams, mole. Which template? I use this one right here, this one.
This one, okay.
So gram divided by mole. Gram divided by mole. And the computer is going to change it to mole -1, but that's fine. As long as it's taking what you are inputting, and there we go. Oh, this time it didn't change it. It put grams per, oh no, yeah, I did. It changed it here, but not there, right? Okay. All right, so we still have a little bit of time, so let me keep going.
The next ones are the same.
The next question is the same?
Yeah.
Perfect. So we're going to skip to the next one then. Number 8. Which of the following is a possible? Okay. So if we go back to our cheat sheet, let me erase this so that you can see the question. So this is one of those word problems that you need to be careful what the question is saying. So which of the following is a possible conversion using molar mass? So using molar mass, we are doing this. So we can convert from moles to grams, we can convert from grams to moles, and that's it. We cannot convert from moles to atoms, or from moles to molecules, or from molecules to moles. That we cannot do. So we are right here. That means grams to moles, and that's it. Which, this is an important thing, you guys. If you have a problem, and we did one, in which you're given grams and you want molecules, you have to go through moles. There's no way of skipping moles. You cannot go straight. So it's a two-step problem. Okay? So I believe the third choice is the only possible one, even though I would be tempted to choose number 4. Let's see what it says. Okay. Any questions about this one? We're going to 9. So this is a word problem. So the oxygen gas in a cylinder has a mass of 360 grams. That means we have 360 grams of O2. We're here. How many moles of oxygen are present in the cylinder? So we're going to convert that to that. So we're going to divide by molar mass. But we need to be careful because we need to divide by the molar mass of O2, not of only O.
So 15.99
Times 2. Yes. This is not atomic oxygen, it's molecular oxygen. So that's the key to this problem. What was it? 30? No, 31. Yeah. Is that it? I don't know.
998. Yeah.
30.998?
31.
31. That's what I thought. 31.998. Okay, so 31.998 is what we're gonna divide the 360 by. So 360 grams divided by 31.998 grams per mole. And look what happens. That cancels and moles come to the top. Okay? If we do it with conversion factors, it's going to show up the same answer. So calculator, 360 divided by, thank you. Point what? 998. 11.25 moles are in that tank. Yeah, I guess.